Okay, this first part is going to be about muscle contraction, and then I'll talk about how it relaxes. So, in this drawing, I'll just go over the anatomy really quickly of the neuromuscular junction. So we have the neuron, and this part of the neuron specifically is the axon terminal. Then we have sodium voltage-gated channels, as well as calcium voltage-gated channels inside. And we have vesicles that contain neurotransmitters, and those neurotransmitters in this case are going to be acetylcholine. Then we have the synaptic cleft, which is just the space in between the muscle cell and the neuron. Right here we have ligand-gated cationic channels. The top of this muscle cell, this top part of the muscle cell is the sarcoplasm. Down here is going to be the sarcoplasmic reticulum. This side, this little tube is called the T-tubule. Then we have a protein called DHP and ryanodine receptor. These two are mechanically coupled and they work together. And like I said, the sarcoplasmic reticulum on top is the sarcoplasm. So when a muscle contracts, an action potential comes down, making the sodium voltage-gated channels open, and that will cause sodium to come in. And then when the inside becomes more positive, then the calcium voltage-gated channels will open as well. Once calcium is in the cell, then these vesicles containing acetylcholine are going to, with the help of the snare protein, are going to bind together, and they are going to perform exocytosis. So the snare protein needs calcium in order to be the binder in this case. So as soon as those contacts are expelled into this extracellular space, or the synaptic cleft, they are able to be bound to the ligand-gated cationic channels. So once the acetylcholine is bound to the ligand-gated cationic channels, that causes them to open, so things such as sodium and calcium can come into the sarcoplasm. That's going to make this more positive. And then here on this side, these voltage-gated sodium channels are going to open and allow more sodium into the sarcoplasm. We have DHP down here and ryanodine. So these voltage-gated sodium channels cause the DHP protein to open, and then these two are coupled together, so the DHP is going to open the ryanodine receptor channel. As soon as that is open, the calcium is going to move outside into the sarcoplasm. And then I'm going to show you that the F-actin before the sodium is out in the sarcoplasm, or has bound to the F-actin. So basically the tropomyosin is blocked the binding sites, and so calcium can't be bound to those binding sites. But we have a calcium-sensitive complex called troponin that will bind to the calcium. So before, there's no contractions, but however, as soon as the calcium goes into the sarcoplasm, then calcium is able to bind to that troponin and release the tropomyosin off of those binding sites. And so contractions are able to happen. And then as soon as the contraction has happened, then we need to be able to relax. So in this process, the neurotransmitters on the ligand-gated cationic channels are going to come off, and we have an enzyme is going to break that down. So the enzyme is called acetylcholine esterase, and basically one acetylcholine will go in there, and choline and acetate will come out. So choline will actually be recycled. So there is a protein that allows choline to go back inside and be recycled. And then as far as getting calcium from the low concentration to the high concentration to be able to help the muscle relax, we need a circuit pump. And so the circuit pump uses a form of ATP to remove calcium from the sarcoplasm. And so calcium is able to go from the low concentration to the high concentration inside the sarcoplasmic reticulum.